coordinates and change a basis. First thing we're going to talk about are coordinates. Suppose we have our basis for an n-dimensional vector space. And let S be that basis. If S is equal to V1, V2, etc., down to V sub n, is an ordered basis for the n-dimensional vector space V, then, and before I say the then, the word ordered means that it matters that V1 is first and V2 is second and V sub n is last. In other words, if suppose n for a moment is just 3. If we have the vectors 1, 2, 3, 7, 2, 4, and 1, 0, 1. And this is S. And S prime has the same 3 vectors, but not in the same order. 7, 2, 4, 1, 2, 3, 1, 0, 1. As sets, they're equal. But as an ordered set, they're not equal. As an ordered set, these are different. Okay? There's a difference between a set and an ordered set. A set doesn't care about the ordering, and an ordered set does care about the ordering. Okay, then every vector V, little v, in the vector space V can be uniquely expressed in the form V is equal to a linear combination of the vectors in a basis. C1, V1 plus C2, V2. Now this is true even if their basis is not ordered. Even if it's unordered. We actually prove this. We actually prove the uniqueness of the linear combination. Where C1, C2 up to Cn, where Ci is a real number. For I equal 1, 2, up to n. So now the coordinates. We can write that V, vector V, in terms of the basis S, we can just say it's the scalars. We can define this to be the scalars. This is in our n, and it is called their coordinates the coordinate vector, excuse me, what am I thinking? It's the coordinate vector of V, the coordinate vector of V with respect to the ordered basis S. These are scalars define V. These scalars define V's. The scalars came from the linear combination of the basis vectors that gave V. Okay. Let's look at this a little bit more closely. Because the idea is to understand this stuff. The more we understand, the less we have to memorize with no understanding. Okay, so if S is a basis and it has the vectors v1, v2 up to v sub n, and you're told that v sub s, the coordinate vector of v with respect to the ordered basis S is C1, C2 up to Cn. Well, this mess just tells me that the vector in there, V, is C1 times V1, C2 times V2, all the way up to Cn times Vn. You might want to think of it as a dot product, okay? You can think of it as a dot product. C1 V1 plus C2 V2 up to Cn Vn. Okay, you need to be able to go from this to this, and you need to be able to go backwards too. That is, if you have this, and you know that the vector V, the vector V's, the V vectors, come from the basis S, well then, this implies that V, with respect to the basis S, the coordinate vector of V with respect to the basis S is the scalar, C1, C2, C3, all the way down to C sub n. And this is in Rn. Why? Because it's a column vector, and it has n entries. Now, what if we have a different basis for V? And this new basis for V is just the reordering of the old basis, S. Remember, S was V1, V2 up to Vn. Suppose basis T has V2 first, V2, V1, V3 next, V4 next, up to Vn. That is, I just switched the first two. Well then, V, the coordinate for vector V with respect to basis S, it will not, with respect to basis t, it will not be the C1, C2 that we had above. Because if we did have equality here, that would imply that V is C1 times the dot product, the first scalar times the first vector, plus the second scalar times the second vector. V does not equal this, plus the third scalar times the third vector on the list. It does not equal this. Okay, now, if I interchange just C1 and C2, C2 first, C1, then C3, and then C4, now we're in business. Now we are in business. C2 times V2, C1 times V1. Now we have equality. Now we absolutely have equality. You have to use the scalars associated with the linear combination. And we know, regardless of the order we write this, we know that V is C1 times V1 plus C2 times V2 plus C3 times V3, etc. up into Cn, Cn. Okay, the bottom line is the order of the basis matters. You have two bases, and they have the same vectors, but they're in different orders. In this section, they're not the same. They're just not the same. Okay. Suppose S is equal to V1, V2, V3, V4 is our basis for R4. Now I define the four vectors, where V1 is, say, 0, 1, negative 1, 0. V sub 2 is 0, 1, 2, negative 1. V sub 3 is 2, 0, 1, 0. And V sub 4 is 1, 1, 0, 0. Of course, whether I put them or not, the entries are separated by commas. Now, let me give you a little v in R4. If little v is negative 1, 2, negative 6, 5, the instructions are to compute little v in bracket sub the basis of S. Compute that. So the first thing we need to do is to write V as a linear combination of the vectors in the vector space. So it turns out that V sub S is going to be C1, C2, C3, C4. It's just going to be the scalars. In order, though, that is, since V1 is first, I better have a scalar times vector V1 first. And then since V2 is second, I better be adding on the scalar times V2 next. And V3 is third, and V4 is last. So I'm not saying we're done. We need to actually find C1, C2, C3, and C4. Now, to do this, you write vector 1 as a column. Here is vector 1 as the first column, vector 2 as the second column, vector 3 in the third column, and vector 4 goes in the last column, and you augment this with V. -1, 2, -6, 5. And if you were to reduce this, you would get the identity matrix, the 4x4 identity matrix. Augmented with the answers. -16, -5, -12, the number 23. So that's C1, that's C2, that's C3, and that's C4. So it's -16, -5, -12, 23. That is the coordinate for vector V with respect to the basis S. It's this. Now, it's forget everything that is boxed. Forget everything that is boxed. That is, if you're given that vector V, the coordinates for vector V with respect to basis S is equal to this, and you are given the 4 vectors, I didn't box those, then you can say that vector V, that is this vector right here, is equal to -16 times the first vector minus 5 times the second vector minus 12 times vector 3 plus 23 times vector 4. They go hand in hand. It's just a neat little way of writing the vector V with respect to a given basis, an ordered basis. Every time I say basis, for this section for sure, I mean ordered basis. Let me emphasize again why it's an ordered basis. We learned that vector V, which was -1, 2, -6, 5. Before I do this, let me write down the basis. V1, V2, V3, and V4. Okay. We learned that this vector is equal to -16 times the first vector minus 5 times the second vector minus 12 times the third vector plus 23 times the fourth vector. Now, suppose I define T to be a basis for R4, which is W1, W2, W3, W4. And I'm telling you, W3 is V3, and W4 is V4, and W2 is V1, and W1 is V2. Okay? So, before I wrote that, I can say that vector V, this is vector V, the coordinates of vector V with respect to basis S is negative 16, negative 5, negative 12, and 23. Now notice that basis T is just the reordering of basis S. As bases, they're equal. As ordered bases, they're not equal, because they're not in the same order. Now, we know that vector V is a multiple of vector 2 plus, it's a multiple of W1 plus a multiple of W2 plus a multiple of W3 plus some multiple of W4. Okay? And our job is to find out these multiples. But now, W1 is V2 plus a number times W2, which is V1, plus a multiple of W3, which is V3, plus a multiple of W4, but W4 is V4. Now, we know that V is uniquely expressed as a linear combination of the vectors in S. But these are the vectors in S, and only the vectors in S. There's the 4 vectors in S. So, it must be that the number in front of V1 must be negative 16. The scalar times V2 must be, the scalar must be negative 5. The scalar multiple of V3 is negative 12. And the scalar multiple of V4 is 23. That is, we get negative 5V2 minus 16V1 minus 12V3 plus 23V4. Okay, but remember, this is W1 and this is W2 and this is W3 and this is W4. So V with respect to basis T is negative 5, negative 16, negative 12, 23. Up to ordering, these are the same 4 numbers that we had over here. But the order matters, because if somebody gives you this, then that implies to you that vector V is negative 5 times W1, which I'll just write W2. I mean, after all, they're equal. Minus 16 times W2, which is V1, minus 12 times W3, which is just V3, plus 23 times W4, which is V4. The order matters. Okay, if you understand it, wonderful. If you don't, try to understand it. But if in the end you can't understand why the order matters, doesn't matter. The order matters, and just live with it. It matters the order of the basis. It's just the way it is. It matters. Okay. So now here's a simple concept, I'm hoping. What if you have the natural basis for R3? Let S equal the natural basis. E1, E2, and E3. Let this be a basis for R3. Remember, E1, since we're in R3, the 1, you have 3 entries, and the 1 is in the first position. Now, the 1 is in the second position. And the 1 now is in the third position. And all the other entries are 0. Okay? Unfortunately, for some unknown reason, we need to do this over. Let S be the natural basis, E1. E2, E3. Let this be a basis for R3. E1, since we're in R3, it has 3 numbers, and only the first entry is the 1 and the rest are zeros. E2, since it's a 2, only the second entry is a 1. The rest are zeros. In E3, all the entries are zeros except the third entry, which is a 1. Let this be a basis for R3. If little v is 7, -2, 4, find the coordinates v for vector v with respect to the basis s. Now, this one is simple because 7, -2, 4 is just 7 times E1 minus 2 times E2 plus 4 times E sub 3. So, call this vector v. So, v in brackets with respect to the basis s is just 7, -2, 4. It's those numbers, 7, -2, 4. So you really, really want this problem to be on a test. And this is going to be the technique for any natural basis, whether it's a natural basis for R3 or R23. Okay, how about the next vector space, V, will be P sub 1. Let V be P sub 1. The set of all polynomials of degree 1 or less, including the zero polynomial. Let S equal V1, V2, and set T equal W1, W2 be bases for P1. So S and T are bases for P1, where V1 is T, V2 is 1, W1 is T plus 1, and W2 is T minus 1. Let V, which is some polynomial, be 5T minus 1. And we want to compute V, the coordinates of V, with respect to basis S, and the coordinates of V with respect to T. Now, just to point out, V1 and V2, they do not match W1 and W2. That is, basis T is not just a reordering of basis S, but that doesn't matter. Now, if you look at S, S is T and 1. This is the natural basis for P1. Okay, why is that? Because vector V, which is 5T minus 1, well, it is 5 times T minus 1. That is, I wrote V as a linear combination of those. is 5 of these minus 1 of those. I mean, if you like, I can write minus 1 times 1. These are the basis vectors. So V in brackets sub S is the scalars. 5, negative 1. Now I want to write B, which is 5 times t minus 1. Now, possibly it would have been clearer if I put C1 and C2. 5t minus 1 is this. Well, I'm hoping it's clear that C1 would be 5 plus C2 times 1, and C2 would be negative 1. But that's just what I wrote down, 5 and negative 1. Now I want to write 5t minus 1 as some multiple of W1, which is t plus 1, plus a multiple of W2, which is t minus 1. Now if I combine like terms, I have C1t plus C2t. That is, I have C1 plus C2t's, plus I have C1 minus C2. That's my scalar. I equate coefficients. The coefficient of the t terms have to be equal. That is, C1 plus C2 must equal 5. And the constant on the left must equal the constant on the right. That is, C1 minus C2 is 5. I just want to write this a little bit smaller. C1 plus C2 is 5, and C1 minus C2 is negative 1. In fact, I'm going to write it down twice. If I add, those cancel out. So I get 2C1 is 4. 5 plus negative 1 is 4. Well, that tells me that C1 is 2. If on the right side I subtract, this cancels. C2 minus a negative C2 is 2C2. And when you subtract 5 and negative 1, you get 6. So C2 is 3. Okay, so now I have the answer. V, with respect to the coordinates of V, with respect to the basis t, well, it's going to be C1, C2. It's going to be C1 first, and then C2. So I found the coordinates for vector V with respect to two different bases, and they're not the same. They're not the same. These two answers, they're not the same. But they still will give me back the same V. In other words, this here tells me that V is 5 with respect to S, which going up to the top is V1 and V2. S is 5 times V1 minus 1 times V2. And if you actually multiply V1 by 5 and V2 by 1 and subtract it, you will get 5t minus 1. This over here tells me, with respect to basis t, V is 2 times W1 plus 3 times W2. And if you, so where's my 2? If you multiply W1 by 2 and W2 by 3, and you added them up, believe it or not, you'll get 5t minus 1. So in that respect, they are equal to one another. Okay. Let's talk about some properties of this vector v in bracket sub some basis. I'll state three properties of v in bracket sub s. The first one is, if you add two vectors and you find their coordinates with respect to basis s, you can find the coordinates of the first vector with basis s plus, and then add to it, that is, the coordinates of vector w with respect to s, and you will get the same result. You have a vector v and you scale it by c. The coordinates of that vector with respect to basis s is the same as just finding the coordinates of v with respect to s and then multiplying that by c. And these two can be generalized. If you had the coordinate vector of c1, v1 plus c2, v2 all the way up to cn, vn with respect to s, you can find the coordinates of v1 first with respect to s and scale that vector, plus you can then find the coordinate vector v2 with respect to s and then do the scaling then all the way down to finding the coordinate vector with respect to s for v sub n and then scaling it. So you should think about why this works. It's not hard. It's not hard. I mean, basically, if in S, V is equal to, just want to see what letters to use. I'm going to use A's and B's. V is equal to A1, V1 plus A2, V2 all the way up to A sub n, V sub n. Well, that implies that V, the coordinates of V with respect to basis S, is A1, A2 up to AN. A1 up to A sub n. And if in, still in S, if W is B1, V1, B2, V2, all the way up to Bn, Vn, that implies vector W in S, the coordinates of W in S is B1 through Bn. Now, if we add these two vectors, V plus W, well, these are like terms. It's A1 plus B1 times V1. Plus, when you add these, you get A2 plus B2 V2. All the way down to, you add these vectors, you can factor out the Vn. Well, this implies that the coordinates for vector V plus W with respect to S is A1, B1, A1 plus B1, A2, B2, all the way down to AN plus BN. But this last vector is nothing more than this plus that. Okay, let me continue up here, please. This vector on the bottom, it's nothing more than A1, A2 up to A sub n plus b1, b2, up to b sub n. Remember, to add these two vectors, first you add the first components, and you get a1 plus b1. Then you add the second components, and you get a2 plus b2. Eventually, you add the last components. You get an plus bn. But here's where it all comes together. This first vector right there is v in brackets sub s plus this second vector b1 through bn, it's right here. It equals w in brackets sub s. So yes, they do match. V plus w in s with respect to s is the coordinates of v with respect to s plus the coordinates of w with respect to s. And all I did was get my hands dirty. I wrote down what v equaled, and then I wrote v with respect to basis s, and then I wrote down the coordinates of v with respect to s. I wrote down w as a linear combination of the vectors in the ordered basis s, and that gave me this. And then I added v plus w I added v and w. So I had a linear combination of the basis in s, so it gave me the coordinates of the vector v plus w in s. It was this mess over here. But this mess over here just happened to be the sum of these two, which equals that. So it's the sum of these two. That was the proof of A. The proof for B is very similar. So now what we want to do is, suppose you have two bases for the vector space V. You have basis S and basis T. You have the coordinates of, so you have a little vector V in the vector space V, and you write V as a linear combination of the vectors in vector space S. So that means that you can write the coordinates of S. Suppose you have the coordinates of vector V with respect to S. So you have the coordinates of vector V with respect to basis S. But you have this other basis T. Is there a way to get the coordinates of V with respect to basis T just from knowing the coordinates of V with respect to S? And what's going to enable you to go from one coordinate to the other coordinate is called a transition matrix. Okay, so for now, we're going to talk about how we get a coordinate basis. Okay, so we're going to have two bases for vector space V. Suppose S equals V1 through Vn, and T, which is W1 through Wn, are bases for the vector space V. Let little v be any vector in V. What we can then say is that little v can be written uniquely as a linear combination of the vectors in T. So V is equal to C1W1 plus C2W2 all the way up to CNWN. Well, that implies that the vector V with respect to the coordinates of vector V with respect to the basis T is just the scalars. We can define a vector just by the scalars now. The scalars of an ordered basis. C1, C2, up to C sub n. Now, we know that little v, is equal to this. Little v is equal to C1W1 plus C2W2 up to CNWN. Okay? Well, if two things are equal, I can find their coordinates. If two vectors are equal, if two vectors in the vector space V are equal, then their coordinates are going to be equal. But now, remember the properties I just wrote down right before I stated this problem? The properties of, I think I wrote V sub S. Oh, coincidentally, that's what I have. This is C1 times the coordinate of vector W1 with respect to S plus C2 times the coordinate of vector W2 with respect to S, all the way down to C sub n times the coordinates of vector Wn with respect to S. Now remember, since V is n-dimensional, since each basis for V has n entries, so V is n-dimensional, this here is going to have n entries. Because W1 with respect to basis S is going to be a multiple times V1 plus a multiple times V2, etc., all the way down to a multiple times Vn. Well, that implies that W1 in brackets will be A1, A2 up to AN. Okay, that's what we're getting. Each one of these Wi sub S's, they're all in Rn. So let me think what to say next. So I just wrote, when I'm erasing, I just wrote down, so you see that these W1 in brackets sub S's are entries in Wn, Rn. Now, let's say, let W1 in brackets sub S, let this equal to, let this equal to A1j, A2j, up to A sub nj. So that means, so now I'm continuing from here. That is, I'm writing down what comes after this. This is C1 times W1. So, oops, I wrote J's. So let me put a J here. I'm sorry. So J is now 1. So I just write down this, where J being 1. This is a 1, 1, A21 down to AN1 plus C2 times W2 in brackets sub S. So now J is 2. So I get A12, A22 up to A sub N2. A sub N2. All the way down to plus C sub N times Wn sub S. So now J is N. So I get A1N, A2N, all the way down to ANN. But now, I want to see where I'm going to write this. That last line, I can write it in a different form. I can write it down as a product of two matrices. The very last line, this mess, all of this mess. This is just the matrix, A1. So the first column of the matrix will be those vectors, A11, A21, down to AN1. And the second column will be the second row of matrix, column matrix, A12, A22, down to AN2. And then, and so on, and then I write the last matrix. And in the end, please make sure you agree that the product that I get is the same as this last line. I'm saying you take this matrix and you multiply it with C1, C2, up to Cn. Do the multiplication. Make sure you get what's on the bottom. Okay. Now, this last matrix on the top right, this matrix is nothing more than our V sub t. That was V in brackets sub t. And this matrix on the left, that's our transition matrix. This is our transition matrix. And we write it as, I'm not clear why the notation is P. I would have called it T for transition matrix, but most people write it like this. It's a transition matrix from T to S. From T to S. If your book uses a different notation, I'll make two comments. One, I'm surprised. And two is, well, figure out the correspondence between my notation and the notation you have. And what you're going to get is going to be the coordinate vector for V with respect to S. Now, remember, where did we get these entries? Where did we get these entries? The answer is with respect to basis T, with respect to the vectors in T, I found the coordinates of W1, which came from basis, was a vector in basis T. I found the coordinates of vector W1 with respect to S. That ended up in the first column. Then I took the second vector in T, W2, and I found the coordinates of that with respect to S. Put that in the second column. And so on. Then I took the last vector in T, and I found the coordinates of that vector with respect to S. And there it is. That is how you find the transition matrix. It takes things from basis T, and it gives you the coordinates in basis S. And let me just make one last comment and erase some stuff. This matrix is called the transition matrix from the T basis to the S basis. From T to S. Personally, I would have written it this way. No. I would have written it this way. From T to S. Why they write it the other way, I don't know. Ask Professor Transition, he'll tell you. So at this point, we'll do a problem. Okay. Let the vector space V be R3. And let S contain 3 vectors in V, and T contains some other vectors, another 3 vectors in V, and in particular, let them be a basis. Let them be bases for V. V is R3. So S set S and set T are bases for R3. Where V1 is 2, 0, 1. Again, you can write these vectors horizontally, vertically. You can write them on this side, but I would stay away from that. Instructions are to compute the transition matrix from T to S. So basically, we want to find this matrix that when you multiply it by vector V, the coordinates of vector V with respect to T, you are going to get you're going to find the coordinates for vector V with respect to S. And what goes in here is matrix P from T to S. So we want to find that matrix. The reason I wrote it down here is I want you to know if you're starting with basis T and you want to end up with basis S. So this matrix, each column of this matrix, well, first we're going to take each vector in T, which are the W's. So this column is going to be W1 in brackets sub S. I'm clearly going to need more space. We want to take every vector in the basis T and write the coordinate vectors with respect to S. So it's going to be, the first column is going to be W1, that came from T, and we're going to write it with respect to S. And then the next column is going to be this vector. And then the third column is going to be this one. And that's going to be the matrix P from T to S, from basis T to basis S. So this is the whole job, finding W1 sub S, W2 in brackets sub S, and W3 in brackets per S. That is the whole job. So we want to write W1 as a linear combination of the vectors in S. We'll call it A1 V1 plus A2 V2 plus A3 V3. And remember, when W1 in S is going to be whatever those three values are. It's going to be that. And we also want to write W2 as a linear combination of the vectors in S. We'll call the scalars B1, B2, B3. We also want to write W3 as a linear combination of the vectors in S. Should be V sub 2, of course. Now, to do the first one, what you would do is take V1, V2, and V3 and write them as the columns. Here is V1, here is V2, and here is V3. And you would augment it with W1, which is 6, 3, 3. Now, to solve the second one, you would take the same three vectors, V1, V2, V3, and augment it with W2, which is 4, negative 1, 3. But instead of reducing this matrix and this matrix, especially when you're reducing the same thing, why not just augment the top matrix with 4, negative 1, and 3 as well? Now, to solve this last system, you'd write down V1, V2, V3, V1, V2, V3, and you would augment it with W3. Which is 5, 5, 3. Well, again, you're already reducing this matrix, which is the same as this one. Why not just augment it with a third vector? 5, 5, 3. That is, if you just solve this top one, you'll be augmenting like 3 vectors in one. 3 matrices in one. You would be solving 3 augmented matrices in one step. A lot better than doing it in 3 steps. And we've seen this before. Now, it turns out that when you reduce this matrix, this left-hand part becomes the identity. And then you get 2, 1, 1, 2, negative 1, 1, 1, 2, 1. This matrix here, that's the one. That's the matrix you want. The transition matrix from T to S is that matrix. 2, 1, 1, 2, negative 1, 1, 1, 2, 1. That is the transition matrix. Let's see if this works. Who knows? Maybe I am completely out of my mind and it doesn't work. So to check that it works, we look at numerical example. We'll look at a numerical example. Okay. So what I think we'll need, so let me put it down, or the vectors. V1 was 2, 0, 1. V sub 2 was 1, 2, 0. V sub 3 was 1, 1, 1. And this made up the set S. And equals. And the set T equaled W1, which was 6, 3, 3. W sub 2, which is 4, negative 1, 3. And W3, which is 5, 5, 3. So I'm going to take an arbitrary vector in R3. Let vector V be 4, negative 9, 5. And I'm going to write it in terms of vector T. 4, 9, 5 is a multiple of 6, 3, 3 plus a multiple of 4, negative 1, 3 plus a multiple of 5, 5, 3. And it turns out that these multiples are 1, 2, and negative 3. How about negative 2? 1, 2, and negative 2. Convince yourself that was correct. So V sub T is, oops, let me write this down correctly. The coordinates of V with respect to T is 1, 2, negative 2. And you should check. 1 times 6 is 6, plus 2 times 4 is 8. That's 14, minus 10. 2 times 5 is 10. 14 minus 10 is 4. Now you have 3, minus 2 is 1, minus 10 is 1, take away 10 is negative 9. 1 times 3 is 3, plus 6 more is 9, minus the 6. It gives you back 3. So, of course, that's a problem. Make sure I wrote these matrices down right. Okay, so let's solve it. We want a multiple of W1 plus a multiple of W2 plus a multiple of W3. It should equal to 4, negative 9, 5. Well, that means we write W1 as a column, 6, 3, 3. W2 as the next column, 4, negative 1, 3. And then W3 is a column. Now, is that where I have my mistake? No. Okay. You write this down as a column, and you augment it with 4, negative 9, 5. I'll leave the first row the same. I'll double each of these columns, rows, and take them away from the first. So here's the first row, and I'm doubling the second row, and I subtract, and I get 0, 6, negative 5, 22. 0, 6, negative 5, 22. And I do the same with the first and the third row. I double the third row, and I subtract 0, negative 2, negative 1, and negative 6. And since everything's negative, I really should have done the bottom minus the top. That is, I'll multiply by negative 1. 0, 2, 1, and 6. Okay. I wish I had the right answers. Okay. I want to switch the second and the third row, because I'd rather clean things up in the second column with the 2 than with the 6. So I have 6, 4, 5, negative 9, 0, 2, 1, 6, 0, 6, negative 5, 22. So I'm going to take row 1, and I'm going to take away 2 of these, because that'll put a 4 there. So I have row 1, and I take away 2 of the second row, and I end up with 6, 0, 3, negative 21. And then I'll divide by 3. 2, 0, 1, negative 7. So I get 6, 4, 5, negative 9, 2. Well, that makes no sense. Oh, that was the first row. I'm so sorry. This is the new first row. 2, 0, 1, negative 7. The second row does not change. Now, I'm going to triple the second row. 0, 6, 3, 18. And I'm going to take away the third row from that. And I get 0, 0, 8, negative 4. And I'll divide by 4. So I get 0, 0, 2, negative 1. Okay. Now, I'm going to clean up that last column by using the third row. I'm debating whether or not to divide by 2 to have fractions, but I just hate fractions. So I'm going to do 2 times the first row, and I am going to take away the third row from it. I get 4, 0, 0, negative 13. So I get 4, 0, 0, negative 13. And I'm going to double the second row and take away the third row from that. Make it 0, 4, 0, 13. 0, 4, 0, 13. And the second row, the third row, I'm not going to change. Now I'll get my ones. I'll divide the first row by 4. I'll divide the second row by 4. And I'll divide the third row by 2. So I get negative a half, which is negative 2 quarters. That way all the denominators are the same. Okay. So hopefully I have the right answer now. If I don't, it is a disaster. Negative 48 plus 52 negative 78 plus 52 minus 10. And this is all over 4. This is negative 26 minus 10, which is negative 36 over 4, which is negative 9. I don't know where I made a mistake, and it's very important that I have this correct so then things work out smoothly. I'm going to make sure I was wrong in the first place. Well, you know what? I have the answer to this. I have the answer to this. Don't know why I didn't think of it from the beginning, but these things happen. Let me clean this up and I'll show you the change I'm going to make. The reducing is very hard because you're doing 100 arithmetic calculations for each reduction. You're going to make a mistake. Now, when I check what I have at the very top, the 4 and the negative 9 worked. Work means I had the right linear combination. But what didn't work was this 5. This gave me 3 plus 6 more minus 6. Well, that cancels out, so I just get 3. Wonderful. Let's call it 3. Instead of calling it 5, let's call it 3. So now it works. V with respect to the basis t is 1, 2, negative 2. That's the coordinates. Okay. So now I claim that this matrix at the bottom left will convert things to basis S. I'm saying that if I take 2, 2, 1, 1, negative 1, 2, 1, 1, 1, this matrix down here, and I multiply it by the coordinates of vector v with respect to basis t, what I'm going to get is the coordinates of v with respect to s. Well, let's see if this is right. When I dot the first row with the first column, I get 2, and 4 is 6. minus 2 is 4. And when I dot the second row with the one and only column, I get 1 minus 2, which is negative 1, minus 4 more is negative 5. And when I dot the last row with that column, since all the coefficients are 1, I just add up these numbers. Because when I multiply each of those numbers by 1s, I get those numbers. 1 plus 2 minus 2 is 1. Now, this is supposed to be, this here, supposed to be the coordinate for vector v with respect to s. And either it is or it isn't. Let us verify that this process works. Vector v with respect to s is 4 times vector s, basis s. It's 4 times v1, 4 times this, minus 5 times the second vector, 1, 2, 0, plus 1 times the third vector, 1, 1, 1. So you have 8, 4 times 2 is 8, minus 5 is 3, plus 1 more is 4, just like we wanted. Then we have 4 times 0 is 0, minus 10 plus 1 is negative 9. And then we have why am I thinking it should be a 5? What is going on? Okay, obviously I wrote down that matrix wrong. One moment, please. Now, the amazing thing is, I'm getting 4 times 1 is 4, minus 5 times 0 is 0. 4 minus 0 is still 4, plus 1 more. I'm getting to 4, negative 9, 5. Somehow, this really is 5. I'm not sure why I'm making this silly mistake. 3 plus 6 great. I was really hoping this would work out nice and smoothly, but something's going wrong. I have a little silly mistake somewhere. I'm so sorry. But again, all I'm saying is if you take the matrix that takes things from t, basis t to s, so it takes things from t, so you multiply it by something with basis t, and you get back something, you get the coordinates of vector v with respect to s. And I found this matrix, it's at the bottom here. I multiply it by the coordinate for vector v with respect to basis t, and like magic, I get back the coordinates of v with respect to another matrix. Okay, where do I get these vectors from? I take the vectors, the basis vectors in t, and I write the coordinates for those vectors with respect to basis s. W1 was the first vector in t. I wrote that vector as a linear combination of the vectors in s, and these are the coordinates. And I did the same for the second vector in t. I wrote down the coordinates of the second vector in t with respect to the basis s. And then I took the third vector in T, W3, and with respect to that vector, I found the coordinates for with respect to S. And this gave me their transition matrix. Now, something silly is going wrong, but that's how mathematics is. I don't see the silly error, I'm sorry. I hope you understood, however, how things were supposed to work out. And just because there's a silly arithmetic error going on somewhere, don't be depressed when you don't ever get, when you don't get a right answer. You just made an arithmetic mistake. Okay, let us look at the following theorem. Let S equal V1 through Vn, and T equal W1 through Wn. The bases for the n dimensional vector space V. Let P from basis T to basis S be the transitional matrix, as I just said, from basis T to basis S. Then, this transitional matrix is non-singular. Non-singular. That means it has an inverse. And the inverse of this matrix is the transitional matrix from basis S to basis T. Just a matrix that goes the other way. You have the coordinates in basis S now, and it gives you the coordinates multiplied by this special matrix, and you will get the coordinates of the vector in basis with respect to basis S. Now the proof is pretty cool. I like this proof. First, we're going to show that this is non-singular. Well, these are a list of ways or equivalences for non-singular. A is non-singular if and only if we have a list of things. One of them says that the null space is always the zero matrix. The null space is always the zero matrix. Okay. We will show that PS from T is non-singular by showing that the null space of PST is the zero vector. some coordinate vector with respect to the coordinates of vector v with respect to t is the zero vector, which is always going to be in Rn. Okay, suppose that's true. Now, what we want to show is that that's had to be the zero vector itself, because v sub t, the coordinates of vector v with respect to t, it is in Rn. I need to show that v sub t is 0. I need to show that that's the zero vector. Actually, it always equals something like this. It has to be all zeros. That is what I want to show. Okay, that's what I want to show. And let me say for some v and v. Okay, but this is always equal to the coordinates of vector v in S. But Ps from t of the coordinate of vector v with respect to the basis t is equal to the vector v in S, always. But we're saying that this is the zero vector. This is the zero vector. Okay? But this implies that, so these are the scalars. Did I say what vector basis S was? Is v1 through vn. Well, that implies that little v is 0 times v1 plus 0 times v2, because v sub s, which is 0, 0, 0 n times, is the scalars. The zeros are the scalars, all the way up to 0 times vn. Well, that implies that v is equal to the zero vector. Let's write 0 sub Rn. The zero vector in Rn. Okay. So v is the zero vector. Okay. So now, let me just think. Remember, every vector can be uniquely expressed as a linear combination of vectors in the vector space. Well, this implies that v, and we're going to turn to basis t now. V, which is the zero vector, is equal to our b times b1w1 plus b2w2 all the way down to bnwn. But if all the b's are 0, it works. That is 0 times w1 plus 0 times w2, etc. to the end is going to give you the zero vector, which is v. But v, or the zero vector, is uniquely defined as a linear combination. That implies b1 equals b2 equals bn, all zeros. Well, that implies that vector v with respect to their basis t is 0, 0, dot, 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 0 is the 0 vector. But that's what we wanted to show. If you take p s from t of some coordinate vector in t and you get the 0 vector, this coordinate vector had to be 0. Hence, p s from t is non-singular. It's non-singular. Okay, so now we proved the first half. Now we need to prove the second part of the proof. In a moment, I'll show you exactly what it says. That is exactly what the second part is asking us to show. Can't show something, can't prove something if you don't even know what it is you're trying to prove. Now, some people might disagree with that comment, but if you have this theorem in front of you, then what I'm saying is true. Then, this matrix P is non-singular. We proved that. Now we want to show that the inverse is the transition matrix from basis S to T. So we know that if we take P from T to S, so we're taking something from T. That's how I never forget to write sub T and not sub S. And I get something here. Okay. This we know. So now I'm going to multiply both sides by the inverse of this matrix, since we now know it exists. P inverse S from T times this is equal to multiplying the left side by P inverse times it by V sub S. Now, matrix multiplication commutes. This is a matrix, this is a matrix, that's a matrix. And I take back what I just said. It has associative property. That is, I can move the brackets or parentheses around. But I keep the same order. Okay, this is the identity matrix. Save a line, identity matrix times that matrix is just that matrix. And it equals to this. Now, don't get caught up here. This is a matrix. I don't care what it looks like. It's a matrix. And when I multiply it by something in the basis S, when I multiply it by the coordinates of a vector with respect to basis S, I get the coordinates of that vector with respect to basis T. So, let me write it up here, please. So, P inverse S from T is the transition matrix from, I take that matrix and I multiply it by the coordinates of a vector with respect to basis S. So from basis S2, and when I multiply these two, I get the coordinates of V with respect to basis T. Okay, so yes, this matrix goes as an inverse, and an inverse goes back. It's fun, right? Let's look at an example. And maybe I can, in addition to showing how the inverse works, maybe I can convince you that the matrix does what I tried to show you it did in the last problem. Let V be P1. The set of all polynomials of degree 1 or less, including the zero polynomial. It's very important that you include the zero polynomial. So we let V equal P1 and let S be the vectors V1 and V2 and T be the vectors W1 and W2 be bases for P1, where V1 is T, V2 is, say, T minus 3, W1 is T minus 1, and W2 is T plus 1. And for part A, at least, we want to compute P T to S, the transition matrix from basis T to basis S. Now, V1 is, we'll call it T0, and V2 will be T and negative 3, the coefficient of the T. And actually, I take that back. Glad I said that word. It's the coefficient of T plus the coefficient of 1, or just the constant, 0. And V2 is 1T minus 3 1s. So it's 1, negative 3. It's 1, negative 3. And W1 is 1T minus 1. And W2 is 1T plus 1. 1T plus 1, 1. Okay. In other words, everything is in the form of T1. That is, 3, 7 means 3T plus 7 1s, which of course is just 3T plus 7. Think about that. In the end, it will make sense. Okay. So now, we want the transition matrix from T. So I need to write the vectors in T with the corners of the vectors in T, in set T, with respect to the vectors in basis S. So I need to write W1 as a linear combination of the Yes, I need to write the vectors in T as a linear combination of the vectors in S. I need to write all of the vectors in T. Now, just the first equation, that will tells me to write vector 1, vector v1 as a column. v1 is 1, 0. And then vector 2 is the next column, and it's supposed to equal to w1. And w1 is 1, 1. But now, this second equation, the right side is the same. First, write down column 1 as a vector, then write down the next column as vector 2, which I already have over here, and then write down w2. So I'll just get a double augmented. This is w2. 1. Now, if you solve this, you'll first get the identity matrix, and then you'll get 2/3, 1/3, 4/3, -1/3. And that's the transition matrix. To the right of the augmented matrix is their transition matrix. So I claim that P S from T is equal to 2/3, 4/3, 1/3, -1/3. Now, let's show that this works. Okay, so I did answer part A. I found it. Now, let us show that it even works. Who knows? Maybe it doesn't even work. Now, what we do is we multiply this matrix. We multiply this matrix by things, vectors, with respect to the basis t. Now, to save a little bit time, 3 times the first vector, 3 times w1, 3 times t minus 1, plus 2 times w2. I'm randomly picking 3 and 2. 3 times, or 2 times w2, is t plus 1. This gives me 3t plus 2t is 5t. Minus 3 plus 2 is minus 1. So that's how, so 5t minus 1. If v is equal to that, then v with respect to basis t is just 3, 2. It's just 3, 2. Now, let's see what happened when I multiply by 3, 2. When I multiply this by 3, 2, I get 6. You get 14/3. And then I get 3 minus 2 is 1/3. This is supposed to be the basis, or the coordinate vectors for v with respect to s. Now let's see if this is true. I take 14/3 times the first vector in s, which is v1, which is t, and then I add on 1/3 times the second vector in s, which is t minus 3, and what I get is 14/3 t plus 1/3 t, which is 15/3 t, where 15/3 is 5t, plus 1/3 times -3 is -1. So it did work. This transition matrix gave me the coordinates of v, 5t minus 1, with respect to s. It's amazing that this works. It's just amazing that we are able to find this. And all you have to do is, unfortunately, reduce the matrix and not make any mistakes. Okay. Part B says to find the matrix that goes the other way. Find the matrix that goes the other way. Okay, that is the inverse of the P matrix. That's the matrix that goes the other way. And instead of calling it P inverse, generally you call it Q. And Q goes from S to T. Now finding the inverse over 2 by 2 is easy. First, you find the determinant. You multiply those two numbers, you get negative 2 over 9. Minus, you multiply those two numbers, you get 4 over 9. So you get negative 6 over 9, divide the top and the bottom by 3, you get negative 2/3. So you're supposed to multiply by the reciprocal of that. You're supposed to take the reciprocal of that, which is negative 3 over 2. And these two numbers, they get interchanged. And the other two numbers, the sign just changes. Negative 1/3 and negative 4/3. And if I keep the half out, that is, I'm going to multiply everything by negative 3. I get 1, 4, 1, negative 2. That's the inverse. This is the inverse. Okay? That is the inverse. And I'm going to be bold and verify that I'm right. If I'm right, when I multiply, I should get 1. The identity matrix. And just for the record, I can factor out 1/3 here. And I get 2, 4, 1, negative 1. So now I'm going to multiply the P matrix by the Q matrix and see if I get the identity. Well, first I could bring out the scalars. They multiply out to a 6. And now I'm going to multiply these two matrices. When I dot the first row with the first column, I get 6. When I dot the first row with the second column, I do get 0. The first row with the second row with the first column, I get 0. And the second row, with the second column gives me 6. Multiply each of the entries in here by a 6. And fortunately for me, I got the identity matrix. Exactly what I was supposed to. So we can now conclude that Q, T from S really is the inverse of P from T to S. This stuff really works. So now we have a way of having the coordinates of vector V in one basis and just multiplying it by a matrix, a transition matrix, and voila, you get the coordinate vectors of that vector V in a different basis. Pretty neat. That completes the section on coordinate and change of bases.